I think that would be helpful. Thanks.
Okay.
Yeah.
All right. So
Good morning, everyone. Thank you for introduction. My name is Mohammad Tahersima, and I'm a member of Nanophotonics Lab at the George Washington University in Washington, D.C. And title of talk for today would be Enhanced Photon Absorption in Two-Dimensional Materials. First of all, like a brief introduction into layered materials. I'm sure you have heard about graphene, a recently discovered material, and we have a whole different families of these materials. One of the most important of them are called transition metal dichalcogenides, which is a combination of transition metals, molybdenum, tungsten, those metals, and chalcogenides, which is sulfur, selenium, and the combination of them becomes like molybdenum, such as molybdenum sulfide, or called TMDCs. This slide specifically shows that we have a really wide spectrum range for these materials, but not all of them are stable, and not all of them are really easy to grow. One of the most favorite of this material is molybdenum sulfide. It was back in 2010 where they exfoliated the ore of this material to 1 atomic thin molybdenum sulfide, and they saw that the photoluminescence of this material enhances 4 orders of magnitude. So just saying that the band gap of the material has changed from indirect to direct, making them really special for optical applications. Also, what they observed is that as you decrease the number of layers, say from 3 layers, 2 layers to 1, you observe there is a blue shift of the band gap. So 1.2 electron volt to 1.9. So you can tune the band gap of these materials, which is pretty exciting. And the reason behind this transition of band gaps is the absence of orbital interaction in the z direction between adjacent molybdenum sulfide layers, which causes this quantum confinement effect. So among all of these layered materials, the most popular of them are graphene, hexagonal boron nitride, and molybdenum sulfide. And they fulfill all different classes of materials. Graphene as a semi-metallic, transition metal dichalcogenides as semiconductors, covering 1 eV to 2 electron volt, and insulator such as HBM. They have exceptional properties. This quantum confinement in the direction perpendicular to the two-dimensional surface of these materials cause really novel electronic and optical properties. You saw in molybdenum sulfide, for instance, there was a transition of indirect to direct band gap optical transition. And for instance, in graphene, you see that the mobility increases significantly. The second is that the surface of these materials are naturally passivated, and they are missing dangling bonds, which makes them really easy to integrate with other materials and with themselves. So you can put these materials over each other, making heterostructures that exhibit really new properties that didn't exist really in nature before. Third interesting aspect of this material is that they are atomically thin. However, they interact really strongly with light. For instance, molybdenum sulfide, having 6 angstrom thickness, can absorb up to 10% of solar spectrum, which is really amazing. So do we have enough of these materials? The ones that we are especially interested in are molybdenum sulfide, boron nitride, and graphene. All of them are industrial. Molybdenum sulfide is used as industrial lubricant. HBN used for cosmetics. And graphite, I think we have seen it in pencils. So I've done a back of envelope calculation here, saying for this graph shows like how many atoms in Earth's crust do we have per 1 million atoms of silicon. So here you see like for 1 molybdenum atom, there are 1 million silicon. We know the number of silicon atoms on the Earth's crust, so we calculate how many molybdenum atoms are there. Knowing the lattice structure of molybdenum sulfide, I've calculated that you can cover the Earth over a billion times with monolayer molybdenum sulfide. So we do have enough of the materials if you want to, for instance, use them in solar cell applications. So previously I just said these two-dimensional methods are great light absorbers, but they're extremely thin. And that is the challenge if you want to use them in photovoltaic applications. And this is the main reason why all the two-dimensional material photovoltaic cells shown today, to this day, have less than 10% optical absorption and less than 1% power conversion efficiency, which is really low, and you cannot really compete with industrial silicon or multi-junction solar cells. So a natural solution would be, well, why don't we make them thicker, putting numbers of these layered materials over each other? So in fact, that is a solution, and we show that, well, if you indeed put 50 layers of molybdenum sulfide over each other, you will have absorption. In the red curve shows that you have more absorption than silicon, gallium arsenide, and the bulk molybdenum sulfide itself. But is it really practical? Well, stacking helps the absorption, but you need to contact each of these layers separately, which is a hell of a job. I would say it's almost impossible. So we thought of a model to absorb light, significant amount of light, up to 90%, and really not make it too complex, not to need many buffer layers, many contacts for each of these layers. So the base, the platform for it was a monolayer graphene as a contact, a molybdenum sulfide as a photoactive material, a photoabsorber, and HBN as an insulator, and a platform. In fact, they're really known for increasing the mobilities of molybdenum sulfide when they're in touch with each other, and probably they associated with decreasing number of impurities in the material when they come to touch each other. So the novelty here is that we roll this stack of them. And why can we roll them? Because they are two-dimensional materials. They're extremely thin. And the mechanical flexibility is one of their characteristics. We roll them into a structure called a spiral cell. And as you can see, we have achieved a multi-layer solar cell. But what's more interesting is that if you put low work function metal, such as aluminum, inside as an inner post, and high work function metal, such as gold, in the outer post, you could contact all these multi-layers with just two contacts, because graphene and molybdenum sulfide are continuous all over the spiral cell. So what we do is that we do an FDD simulation of the cell to see indeed it behaves as we want it to. And we study the optimal lengths for the spiral cell, the optimal diameters, and the thickness of the insulating HBN. The lower figure here shows the generated electron photons. As expected, on the thin, you see the thin layers, these thin circles represent molybdenum sulfide and graphene. Those are the photoactive materials, which you expect the electron hole be generated in those. And the blue part are actually HBN. We didn't expect any excitants to be generated there, and in fact, there were no. And so there are two figures, right? One, you go to the source, one you go to the back contact. So as you travel, as the light travels into the structure, You can see that electric intensity, electric field intensity gets lower, and the photogeneration decreases. That proves that, well, as the light travels into the cell, you have generation of electron hole pairs. For the thanks. So this is a little noisy figure, but for a good reason, I guess. So the red curve corresponds to the red rectangles, and the green one corresponds to the green structure and green model profile. Each of these peak values, 1, 2, 3, 4, 5, 6, is the modal profile for 1, 2, 3, 4, 5, 6, right? So the red goes here, 1, 2, 3, 4, 5, 6. And the disk is the cross-sectional mode profile, and the dashed rectangle is the longitudinal mode profile. So what we observe is that the spectral scan here, it displays that the resonant-like fringes in the absorption spectrum, which is associated with the nanocavity resonance. We also find that for the core shell structure, which has metallic cladding, we see the fringes to be more visible. And this is due to optical field confinement inside the structure, of course. The higher Q factor observed in the core shell cell relative to the spiral cell, which is completely dielectric, are clearly visible in the cross-sectional mode profile as distinct power lobes. You see, like the power lobes, the mode lobes here for the core shell structure is clearly more visible than the dielectric, and that's the optical. Right. So we analyzing the resonance peak spacing from previous observation graph. We see that we plot the inverse of the nanocavity length and the mode spacing, and we indeed see a linear behavior. And there we could prove that that is a fabric per cavity behavior. Also, this is the spectral current density. We have calculated current density by integrating it over the 30 nanometer to 800 nanometer wavelengths of 37 milliampere per cubic centimeter, which is several times higher than silicon nanowire and about twice the silicon photovoltaic cells used in industry. Also, with optimizing the thickness of the insulating HBN, we could reach, we defined an enhancement factor, which not only depends on enhancement of the absorption of the material, but losing less photoactive material of molybdenum sulfide and graphene to the total density, total volumetric material that is used in the solar cell. So as a benchmark, the goal for us was, well, the efficiency, which is the goal of every photovoltaic cell industry. However, we also wanted to aim for power density and using less material for what we observe. And I think this is a goal, at least numerically, achieved. Well, thank you very much. Which figure are we talking about? Okay.
The spiral, I would imagine the boundary conditions on that are really tough for scientists and time to make it so it's 2D layers like continuously stacked on another. You know, what you were seeing was like physical or any calculation to like match that, what you saw with science and time to make?
You mean for the dielectric cell rather than the core shell cell?
Yeah, I'm just wondering if like that's what you expected or that was like surprising result.
I think this is like pretty much expected. You see, like for instance, as you go, you have a blue shift in the wavelengths, you will have less. How to say? For instance, you move from dipole to quadrupole and double quadrupoles. So I think that like is something expected. One thing, like for instance, for boundary condition, I could tell you that all over the place we have used perfect match layer. So like any light that goes out of the structure will be gone. Like it doesn't bounce back to the simulation. But pretty much like one thing that like surprises us still is that why would well, this is the like z direction is propagation direction, right? In all of them we see focusing effect. We're not really sure why would that happen. Yeah.
So this is not my field of research, but I was just wondering, if you go back to one of your initial illustrations of the spiral cell, it seems to me there's not, like a gap through like after you go around the first like rotation, there's a gap of what I assume is air. What do you know if that has any effect on, like, if you included that in your simulation or experimentally that has any sort of effect? It just is interesting to me.
No, in the simulation we precisely simulated like this structure with the gap, including the gap. However, like I really assume like if we want to do like show it in experiment, we would rather use for the first contact we would use a multi-layer graphene, and for the last contact we would use multi-layer molybdenum sulfide. It's just that it's been shown that they have better contact qualities when you have multi-layers of them.
Okay.
So like we haven't done the experimental work yet, but it's something we have been trying to do. So here, like you can see that this is molybdenum sulfide, right? And we could indeed roll them by like introducing like lattice and thermal mismatch, but we haven't completely achieved the final structure yet.
There's a speaker